today I want to talk about basically some new stuff. So the talk will be, you know, it's a talk done over the weekend. So it's probably going to be a bit harsh, but I want to talk about some new results on topology and magnetic topology. And if there's anything that you get from this talk, this should be the 4 websites presented here, because all the results are actually on these websites. The magnetic one is not, it's so far a French website, but it will be .com very soon. But if you want to go to the magnetic one, just make sure that you type in .fr. Okay, how do I get, okay, cool. So, of course, the collaborators, since they're the ones that did most of the work, is the magnetic stuff is basically done by Sue Wieder, Song, El Coro, and Nicolas, and of course, the other collaborators, Vernieri, Bradlin, Chen, and Felser, are instrumental in the first part of the talk. So, here's a list of the things that I want to go through. I'm not sure I'll be able to go through all of them, but basically I wanted to give you a hint of what, you know, the theory behind what we're trying to do and how this theory basically needs to get adapted for obtaining magnetic topology. And then I want to show you several calculational methods and several programs that we basically developed in order to implement this you know, purely analytical theory to materials. And I want to show you some topological phase diagrams obtained from high throughput calculations of non-magnetic and magnetic materials, present some databases that we've created in this long-running program, and show you some ideal topological materials in new systems, and show you somehow a sort of not necessarily incredibly successful yet, but certainly promising machine learning techniques to not discover new materials, but predict topology. Okay, so this is the, sorry?
Keep going.
Okay. I thought there was a question, but I guess it was just my feedback. Okay, so discovering topological materials has kind of undergone several waves of progress, starting with 2006. And now basically what people have sort of started to understand, it's become obvious, is that topology actually presents a way of classifying compounds that was previously unknown. So of course we got elements in the periodic table, but with all these elements, we can form compounds, and then the number of materials that we can form increases basically factorially. And you know, we need some sort of classification scheme to put them in some sort of order, just like the periodic table of elements is. And this classification scheme I want to claim is basically topology, which allows us to classify compounds based on adiabatic continuation. So different topology classes basically means different compounds, or if they're insulators, that certainly cannot be adiabatically continued to one another. And the compounds that have the same topological class represent compounds that could be adiabatically continued to one another, and hence represent sort of at zero temperature the same ground state. For semi-metals, it's a different story, but it's basically the same thing, saying that a topological semi-metal cannot be made into an insulator without, you know, breaking some symmetry or going to a different ground state. So you can think of adiabatic continuity, which is you know, usually for insulators, as some sort of a more general principle in this sense, also available for semi-metals. And this is an array of the topological materials that have been discovered, but in order to put in this array, basically you have to go to this of what a material is, or what information do we actually have about a material that's you know, say universal. And really the information that we have in a database, or in you know, the first thing that we do when we find a material is to look at its symmetry structure, the symmetry group that it lies in. And this brings us to the 230 non-magnetic space groups, very soon in the talk we'll have 1651 magnetic space groups, but the 230 magnetic space groups are basically tabulated, and every material that's in database belongs to one, if it's not an alloy, etc., belongs to one of these symmetry groups. And these space groups give you unit translations, which are given by the size of the unit cell and the lattice translations, the group operations, the non-symmetric groups, and they give you the atoms in some lattice position. So now the question is, given this information, what's some sort of a universal information that we can get, or universal classification that we can get about these atoms? And the first thing that we want to do is we want to establish a link from real space orbitals to electronic bands that doesn't involve Hamiltonians, that doesn't involve some sort of quantitative energy information, or some sort of hopping parameters, that just involves only symmetries. And this would be very powerful and very universal. And this type of link actually exists, and it's called a band representation. This is the link that basically gives you every type of band that you localized orbitals. So hence, if it starts from localized orbitals, we'll call it atomic limit. So these band representations are sets of bands linked to localized orbitals that respect all these crystal symmetries and, for example, time reversal or others. And the strategy of this program that we and others have been developing for basically years and years is to classify all the atomic limits, which are so-called boring. We'll see that actually, maybe not in this talk, but there's atomic limits that are not boring also. But to classify all the atomic limits, and having classified everything that's boring, you can then go and ask what is not, information about what is not boring. So everything that's not an atomic limit is going to be topological in our sense. So how do we classify all the atomic limits? Well, this, I don't have time to go through details, but this is actually a mathematical precise statement, which is representation induction. And what you do is, roughly, you start with a set of symmetry groups. So for example, many ways of rearranging the atoms. Here you have 3 ways that have the same symmetry group: the triangular, the honeycomb, and the Kagome lattice. And they have the same symmetry group, but there's 3 different ways of arranging the atoms, which represent basically 3 different Withou positions at which we put the atoms. And then within the same lattice, we can have different orbitals at different lattice sites. So for example, if I pick the graphene or the hexagonal unit cell, I can have S or PZ orbitals, or I can have PX and PY orbitals that are relevant or that are sort of close to the Fermi level. And these will give you different band structures, but they're all given by symmetry considerations. And out of these, the representation induction basically means that I can pick, given a symmetry group, a lattice, and a set of orbitals, I can immediately give you the bands and the representations in the Briand zone after some Fourier transforming and after some machinery that can be automated, well, analytically derived and then automated for every group. One can give you the bands that come from a set of localized orbitals. And what do we mean by one can give you the bands? Well, the 0th order that one can give you is the eigenvalues of these bands in the Briand zone under the symmetry operations that keep a momentum invariant in the Briand zone. So for example, just by knowing that I have bands that come from S or PZ orbitals in graphene, I could immediately infer that there's a Dirac point at the K point in graphene, which is the representation K3. So I don't need to know anything besides that. But for example, if I have PX or PY orbitals, I would be able to tell you that I don't need to have only a Dirac point. I could have, for example, a single value degeneracy, which is K1 and K2 at the high symmetry points. And so far, I've used no Hamiltonians. Okay, so the moral of the story is the following. So now, say you do this for every space group. So kind of what I said was very general. I didn't particularize to any space group. So I could take any space group and look at all the kind of orbitals that I can put in at all kinds of positions and infer the bands that come out of those. And those would be trivial bands. And it turns out that if I stack up orbitals, so for example, I'm asking say I have an S and a P and a PX and a PY orbital at let's say hexagonal lattice on the graphene sites, and ask what are the bands that can come from them. Well, it turns out that these bands kind of decompose into a set of elementary bands, kind of like reducible representations decompose in irreducible representations. And an irreducible representation for a band is called an elementary band representation, and is defined by induction, or sort of representation induction, from a maximal Wyckoff position, and from the irreducible representation of that maximal Wyckoff position. So for example, in graphene, the two sites are A and B, the Wyckoff position of multiplicity 2, and the bands that are induced from their by the S and P orbitals, or S and PZ. The S and PZ orbitals, for example, are the same representation, reducible representation, if I don't have mirror symmetry in the graphene layer, and the bands would basically be the same. So if I want an S and a P orbital, PZ orbital bands added, they would basically be twice times an S orbital band, and I could basically stack them up, kind of forming a linear space. So the concept of band representation was introduced for several groups by Michel and Zach, or several works by Zach. And what we did is basically to extend this concept to symmetry groups and all symmetries and time reversal. But moreover, Michel and Zach had this paper said that elementary energy bands in crystals are connected, which basically, if you follow the logic to the extreme, means that there is no topology. Now we know that that's not true, that there is topology. And in fact, all the bands that are not atomic limits are topological. And this is basically how you define topology, as the bands that are not an atomic limit, the bands that are not an EBR. And this relates back to the work of Solianov and Vanderbilt, basically that showed that quantum spin Hall state cannot have Wannier states that respect time reversal symmetry. So let me show you how you use this to obtain information about crystals. So imagine I have two-dimensional inversion symmetry on a square lattice, and the atoms are at the black stars spots in my slide. That's where the atoms are. But the center of charge is quantum mechanical and can move anywhere. And there's 4 special points in this unit cell that are invariant under some group that's isomorphic to inversion symmetry, just inversion symmetry. So obviously 1A, this black star, is invariant under inversion. 1B is invariant under inversion times of X lattice translation. Why isn't this working? Let's see. Okay. 1C is invariant under inversion times a Y lattice translation, and 1D is invariant under inversion times an X plus Y lattice translation. So now all these symmetry groups are isomorphic, but they're different because they have a translational part which is different. So their representations in momentum space are going to be different. And these are the atomic limits. So what type of representations can inversion have? Well, it can have a scalar, which is an S orbital, and a vector, which is a P orbital. So I can put on each and one of these sites an S on a P orbital to have 8 atomic limits in a 2D lattice with inversion symmetry. And these 8 atomic limits are S on P orbitals on 1A, 1B, 1C, and 1D high symmetry positions. And because of these translation operators, the induction procedure, the way it works is, I've said that given an orbital and a position, I can tell you what are the eigenvalues of bands in momentum space. And let's go through this procedure for the S orbital. The S orbital sitting at 1A has, it's a scalar under inversion, has only positive eigenvalues in real space. It has no translational symmetry as a site symmetry group, it just stays invariant under inversion. So when you Fourier transform it to go to momentum space, it's going to have plus eigenvalues under inversion. The P orbital at the 1A Wyckoff position is a vector. It's got negative eigenvalues in the inversion. Now, if I go to 1B, however, the S orbital at the 1B Wyckoff position has a translational symmetry in its symmetry group, because inversion sends it to minus 1B, and I need to translate it back. That translation gets represented in momentum space by e to the ikx, and e to the ikx is -1 at the x and m points. So the S orbital has plus minus, as you can see, at the gamma x, y, and m points eigenvalues. You can go through this procedure, and what you find immediately is that there's only, in any atomic limit, there are only even number of negative or positive eigenvalues of the inversion operator at high symmetry points. So now, if I have a band that has the following eigenvalues, only odd number of eigenvalues, of negative inversion eigenvalues, so for example, a minus inversion eigenvalue at the y point, and I have to prove you that this band exists, but I don't have time to go through that, but it does exist, then this band cannot be an atomic limit, and hence it has to be topological. So now, by the generality of this prescription, it's very clear that you can get all the topological bands, even with just zeroth order information in all the non-magnetic symmetry groups for all compounds given a set of eigenvalues. And this is basically all these atomic limits are tabulated on this website that we built. There's 10,398 atomic limits, and anything that's a material that doesn't decompose in its atomic limits has to be topological. And this is some information that you can get on this website. Okay, so this is basically saying, this slide is saying that if I find a band that I cannot decompose in terms of elementary band representations or atomic limits, then it is topological. And what you can do now is build this huge high throughput search. But before you do that, you need to build some more tools that aren't available yet, that weren't available in at least the ab initio program. So the way this high throughput program works is you get a material, which from the database, you have its symmetry group, lattice structure, etc. And then you run a DFT code to get the wave functions at high symmetry points. Now, for VASP, for example, the DFT code doesn't give you the characters of a non-symmetric representation. You have to build an extra program that gives you the characters of the symmetry eigenvalues of the non-symmetric operations in the Briand zone. And that's called VASP to trace, this program that we build that's basically available now. You take any non-magnetic material and you run DFT, you find its eigenvalues, and then you find, this program finds you the trace. You find the wave functions, the program finds you the trace of the eigenvalues. Once you know this, you have to build another program called check topological matter, which basically runs this eigenvalues, compares them to the atomic limit, and gives you a yes or a no, whether it can be represented an atomic limit or not. And this will find you all the topological materials. And the result is that basically about 45% of the material are of the get into a discussion about what that means. That's why I didn't say materials, I said materials / bands. But basically, there's a huge amount of topology in materials, and if there would be only 5% of the materials that would be topological, there would be no way of making a characterization of materials that is topological. So the fact that there's a lot of them means that you can actually characterize materials by their topology. So what's a result, so you can say, okay, well, you have this program. What's the first interesting thing that you have out of this program? Well, the first interesting thing that we got was bismuth, which, even though we didn't present this way, was obtained in this way. And bismuth is basically a high order TI. So up until bismuth, it wasn't known that you can have a gap bulk, gapped surface states, but a gapless hinge mode. And bismuth is really the first material that you can say that even though, it was thought to be trivial for a long time, it has Foucault index equals to 0. There's another topological property in it that basically from DFT is obvious. You can see the atomic limits on the right upper table and the DFT eigenvalues on the right lower table. It cannot be written as a sum of EBRs. Okay. For example, the other thing that you can see also for bismuth is the following. You can ask, if I have a DFT calculation, you can ask how many of the bands in this material I will need to invert or switch around to get to an atomic limit. And it turns out that in bismuth, the answer is all of them. So we compute the bands from the inner shells all the way up to, say, 10 electron volts above the Fermi level. And it turns out if you look at each band separately, each band is topological. So you cannot, so of course that doesn't mean that, if I add 2 topological bands, I get something trivial, but each band is topological. So it would mean that to get bismuth in to make transitions from bismuth to atomic limit, you will need to actually flip all the eigenvalues of all the bands. So, the fancy name that we found for this is super topological, but we can find other names if you don't like it. So, turns out there's about 830 compounds showing this super topology, about, I would say 1% or 0.5% of the compounds. And, you know, they're all on this database, which is kind of a sneak preview of a new database. The database already exists, but this nicer user interface doesn't exist, where the compounds, you can go get the compounds, get them with or without spin orbit coupling. You have dynamical plots, etc. You can get the band structure, and you can get all the high symmetry. You can look at every band and find the index and the topology of every band. And for example, that band was a fragile topological band. You can get the representation below the Fermi level, and you can get many things about the materials, including, you know, their properties without spin orbit coupling, and including a search based on indirect band gaps, which are not given by that's information that's not given by topology. Okay, so having done that, I want to move on to the magnetic materials, which is really kind of the new stuff. But basically, the program runs in the same way. You have to find the magnetic symmetry group and of a material. But in this case, the program is much harder. And there's a reason why it's much harder, because even if the mean field theory, for example, that you kind of assume these materials in order to get the electronic band structure is valid, even if the magnetic order is measured, which is not in many of these compounds, and even if the magnetism is commensurate, it's still very hard to determine topology, because first you must compute the electronic structure, and then you must have a theory of magnetic topology. And just because of the sheer number of groups that's much larger than the non-magnetic ones, it turns out that once we went through this approach, it turned out that not even the full representations for magnetic groups were derived. So, for example, just to give you a little bit of a flavor, so if you look at the two magnetic orders that I show on the screen, the left magnetic order and the right magnetic order, even though one of them is, you know, completely anti-ferromagnetic and the other one has a ferromagnetic order, have the same magnetic symmetry group, for example. So magnetic order is not equal to the magnetic symmetry group, and so there's, you know, in this simple case you can see it, or we can go through it, but in more complicated cases, obviously you need a full algorithm to do it. And the other things that were very that were not known is the full magnetic co-reps, or the magnetic representations in momentum space. The magnetic compatibility relations, the magnetic trivial bands were known, and the magnetic topological indices were known, although a group structure of them was known here. Okay, so what we did is we ran this program for all the magnetic groups, and this is going to be available soon online. There's 33,000 magnetic atomic limits, rather than 10,000 non-magnetic ones. And we now have all the symmetry indicators for all the magnetic groups, and we know what they mean. So how do you run a high throughput on this? You go to the Bilbao crystallographic server, and you look at the mag data database. Now, the good thing about this mag data is that it's got information that comes from neutron scattering rather than calculations. So you know that, you know, within experimental correctness, it is correct, and you have their magnetic structure. So they have, for example, these CIF files that look like this, and what the magnetic structure is known, and the magnetic moments are known. So then you can do more accurate calculations. And this is what we did. So we did several calculations, Hubbard U, and we obtain functions at the macro k vectors at the high symmetry points. And then after you do this, you need to do two things. Again, you need a program that gives you the trace of these for all the magnetic symmetry groups, which we have. It's called magnetic VASP to trace. And then you need a program that gives you the topological indices. I don't have time to go through this, but all these have been done. And the topological phase diagrams for the different values of U were obtained. So basically, these self-consistent calculations show the following. Now, the magnetic data, the ones, so magnetic means anti-ferromagnetic really here. So it's much smaller because we're only looking at the ones where the neutron scattering data is known. So there's 403 materials of 549 that actually convert with LDA plus U, and there's 130 materials, which is basically sort of the same proportion, which are topological for at least one value of U. There's 50 of them which remain topological for all values of U, and you can read these things. So let me give you some examples. So for example, plutonium bismuth is a axion insulator with quite a large gap, LDA plus U, and this remains the same for all the values of U that we tried. Then, you have magnetic Dirac semi-metals, and this is, for example, Dirac nodes protected by some C3 symmetry, which don't have to be at the same energy, unlike in the time reversal invariant case. And you have Wien nodes in this system and some other Dirac nodes. So the full extent of topology is just being analyzed now, but there's certainly new materials in the antiferromagnetic database. Okay, so what I wanted to end with in 1 minute is machine learning. So what we did here is, we have this big database of non-magnetic materials. So we wanted to know, can we predict topology without doing calculations? And I have to emphasize that this is not predicting new materials. It's just having a new material and predicting topology without doing the DFT, which for some materials that have 100 atoms per unit cell, that's actually quite an improvement, because machine learning would do it in a fraction of a second, whereas a DFT for 100 atoms would run several days on a supercomputer, or for more than 100 atoms per unit cell. So, for example, what we encoded here is the number of electrons, the symmetry group, the chemical structure, and the atom position. And really, as an output, we didn't output the topological index, we just outputted coarse-grained information, whether the material is trivial, a TI, or a semi-metal. And the training is 32, and the testing is 2.5 for testing. So the results weren't as phenomenal as we thought, but they were encouraging, and we're still waiting. We're still trying to figure out what more information we need to add to the data set, or what more to the training set to get a higher proportion for a higher accuracy. So for semi-metals, for example, and for trivial systems, the accuracy was quite high, so about 90%, but for TIs, it was about 70%. So we sort of understand why this is true for semi-metals, because semi-metals, sometimes only the electron number will tell you if there's a semi-metal or not in some symmetry groups, but we don't fully understand why we can't get to, say, 90% for TIs. One of the reasons might be the fact that even though these are still small samples for machine learning techniques. So with that, I wanted to close, and thank you for your attention.
Thank you, Andrei. Any questions? I had one question, that the 45% number you gave for the number of materials that were topological in the survey, what's roughly the breakdown of like fragile versus strong crystalline?
So that's a very good question. So there's no fragile at the Fermi level. There's about 10% are 10% or 11% are insulators, are TIs. About the remaining 12% TIs, the remaining semi-metals, which can be line, nodal, etc., plane, etc. But there's no fragile at the Fermi level. Now there's many which have fragile bands, and if you're asking, say, like if I look within plus or minus 10 electron volts around the Fermi level, if you're asking what's the proportion of materials that have at least one topological band, fragile or otherwise, within plus or minus 10 electron, which is roughly our energy window, that's about 97%. So basically, band characterization has to be topology, and it's everywhere.
So Andrei, if you could get the identification of topological, if that characterization extended to a broader category of materials then what would that buy you?
Sorry, can you repeat the question, because you're closer to the mic?
Why don't you just stand up here?
Sorry, Mike, can you repeat the question, because you're closer to the microphone?
Right.
Oh, okay, great, thanks.
So if you could get your identification of topological insulators using your machine learning algorithm up to 90% from 70%, and if that held for a broader set of materials than your existing database, what would that buy you?
Well, so that's a good question. So far, I'm not sure what machine learning would buy you, with the exception of, so we put this program online, and what it would buy you is that you wouldn't have to run the DFT, or if you had, if you had a new material with 100, there's a lot, we weren't able to do calculations with more than 70 atoms per unit cell because they were too expensive. So computationally, we already had 40 million CPU hours that we computed these below 70 atoms per unit cell. So what it would gain you if you had 90% is if you have a material with a large number of electrons, you would know whether to run the DFT or not, whether it's likely that it's topological or not. Now, really, the kind of holy grail in this is to do material prediction, but that's that's probably going to involve phonons and stability, which I do think topology plays a role in phonon band structures and instability, but in ways that we haven't figured out yet.
Okay, I think the remainder of the questions we'll keep for the discussion. Thanks, Andrei.
Thank you.